Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We were looking at interferometry for measurement of flow with density changes. I'll just go back and look at that picture once of the flow field of the setup. I made one small slip which I want to correct right now. Typically I did not tell you what the light source was. That was the mistake I made. I'm having a parallel beam of light coming. I said I'll put a mirror. This is a beam splitter which splits 50% of light or whatever, some fraction of light this way. Another mirror. And the final output will be a mixture of these two together. Again there is a beam splitter which will recombine this beam and this beam together, and at the end I will put a screen here. I will be watching what happens on the other side. From this side I will be watching. If it is a screen, I will just look from that side. So in this overall scheme I did not tell you, I just slipped that this should be a coherent light source. Okay, coherent light source, that is it is supposed to be something that has only some fixed phase. That is, it should be all the light waves that are coming in should be having the exact same phase. Why? We are thinking about looking at the phase difference. Okay, so phases are important for this. So typically we use lasers for this. Laser must be the source for this, and after that we expand the beam to whatever size we want. From there we will split it into two pieces. I will put a setup, my flow facility somewhere here, say a jet or something. If I have a jet in there, then that jet will deflect, not really deflect the light in this case, it will just slow down the flow of light through this. So the light, when it goes through this, if my jet is say helium jet, then I am lighter than air. So if density is lesser, refractive index is lesser, which means it will go faster. So this light going through here will go faster, while the one going through the other path will go slower. Because of that, there will be a phase difference at this point. After that they are mixed together, and when they come here, because of the phase difference there will be interference change. I said change because initially in the alignment, if we adjust everything such that every point on the mirror wherever the light comes in, every light ray, if I think about, each of these rays, if they come and meet exactly at the same phase here, then there will be no interference at all. Everything will be exactly same intensity. Typically what we do is we adjust it slightly off. Either this is rotated this way, or rotated this way. If I do these, I can get some fringes directly on this, because if I made it go, I will put a dotted line here. If I make it go like this top ray is taking a shorter path, okay, while the bottom ray is taking a longer path. I am imposing a known interference here. Typically I will create a set of fringes. If this is the case, there will be interference fringes this way, perpendicular to this board. There will be lines like this on the screen. Okay, that is what you will see from here if we have this way. If I have the other way tilt of the mirror, then I will have the line that is going away from the board will have one face, while the one going on the board plane will have some other face. When it comes here, now I will have vertical lines here on the screen. Okay, now I can choose whichever setup I feel like, or I can choose partially vertical, partially horizontal, then it will get a slant lines on the screen. Anything can be possible with just adjusting one mirror. Okay. But first what we will do is typically we will adjust such that everything is exactly parallel, then we will adjust it slightly off the good alignment, so that we get reasonable fringe settings. Now if I put with horizontal or vertical some such slant fringes already, I put a density gradient here, density variation here, then there is going to be a change in the fringes. Now the change in the fringes can be related to if my fringe pattern was like this. Say there are lines like this. This is my original fringe pattern. From here, if it moves to if it does something like this, then if we track this particular fringe, it has shifted down. Now this shift can be exactly related to the density difference. Okay. How much did this fringe shift? From here it went by one order down, okay, one fringe down. If it went two fringes down, then it may look something like this, more dip. Okay. Depending on the number of fringes down, I can tell that can be related to delta rho. Delta rho, that particular ray is seeing, that is what we will be picking up. That is the idea of this method. Okay. This much of detail is enough, I think, for this. We will just go and look at some images of interferometry which we did in our lab. I will go to the screen. Here we have this, which is just no density gradient, it is just aligned such that there are vertical fringes here. We are using a red helium neon laser, so we are having red lines vertical, bright and dark, etc. And in this image we have put a soldering ion. This black shadow is the soldering ion. Of course, it is not full shadow because part of the beam has it, the other part of beam will still go through without being blocked by the soldering ion. Okay. So one beam we have it, and the other beam we do not have it. Now this is the soldering ion which is getting hot slowly. We turned it on, and what we are seeing is these fringe patterns are no more the same. See that there is gap in the fringe pattern changing. Okay. That basically says that these fringes have shifted this way in this particular case, which means I am going to have some kind of density variation here. You can see that far away the fringes are not changing much, but as I come closer they are getting expanded more. Okay. So there is some kind of changes happening in here. We go to the same soldering ion thing with horizontal fringes. This case we adjusted the mirror such that you get roughly horizontal fringe pattern. It is not exactly parallel, you can notice, that means there is a irregularity in my mirrors. With this, when we put soldering ion, the same, this is the shadow for the soldering ion, this sitting here, where we are seeing that all the lines are being pulled down suddenly. Yeah, all the lines are being pulled down, saying that the density inside is lesser suddenly in this particular case. We have arranged it such that it will be lesser density in here. Okay. It can be arranged the straight opposite also depending on how you arrange it, but I know that in this case density is getting lesser and then going back to normal. Okay. It's here it is same as this height. If I follow that line, instead of going and ending there, it is going down, coming back out and then ending there. That says that there was some density variation in this region, and similarly on this region. Everywhere around this hot metal rod you are going to have a difference. Now we did the experiment with helium jet. I have adjusted, this is not the same setting as the other horizontal fringes. I adjusted such that it can be opposite now, where now we are having fringes again horizontal, we readjusted it, and then we put a small metal tube with a tiny hole where there is helium jet coming out of it. You can see the jet boundary like this here and here, and everywhere inside the jet boundary there is a jump in the fringe. Okay. And that can also be used for telling density difference. The same helium jet now we are doing with cross slant fringes. Depending on what you want to show in your images, you can choose the fringe settings. If you choose slant, you can now see that I have realigned it, now it is going down as density decrease. You are seeing that it is from here, go down and then come back to the original line and go out, which means this line is my jet boundary here, and this line is the jet boundary here, and this region is your metal block from which the helium is coming out. Okay. That is all you can see from here. We already have seen other density based visualization methods, right. We looked at shadow graph first, then we looked at Schlieren, and now this is interferometry, and I think that completes pretty much every kind of visualization method which we have for compressible flows, which are simple enough to deal with. There can be other methods which we won't deal with currently. These are specific to density change based methods. Now we will move on to computational methods used in compressible flows. One of the most popular ones, and they are simple enough method, happens to be method of characteristics. We will deal with only method of characteristics this time in this course actually. Method of characteristics is for a problem which is two-dimensional, steady, irrotational, isentropic, okay, supersonic. These are the standard conditions. Of course, other than this, I will say that the flow is inviscid, no body forces, no friction, the friction and no inviscid are the same thing, no heat release. Those kind of assumptions also will include in this. Okay. So, I am just thinking about the standard set with these extra conditions in here. Okay. This is the only case where I will be solving my flow field currently. Only this type of flow field I will be solving. If I think about it, I will start with the equations of motion, mass conservation. It is dou by dou xi rho ui equal to 0, or you can rewrite this as, this is from fluid mechanics of course, which you can rewrite as ui dou rho by dou xi plus rho dou ui by dou xi equal to 0. This is one expression, that is mass. Next we will write momentum equation. Momentum equation again I will write in this index notation. Later we will switch to, it is 2D, right, we can always switch to UV coordinate system. We will go back to it after some time. First we will write the general thing. Anyway we will switch in 2-3 minutes probably. We will just simplify it a little bit. Dou by dou x j of rho ui uj equal to minus dou p by dou xi. This is your I momentum equation. If you think about it, I can take 1, 2, 3 values, that is how it comes out, which along with this expression can be simplified a little bit. So, I am going to keep this rho ui together, uj and multiplied by rho ui. I want to do differentiation by parts. If I do that, I will get rho ui dou uj by dou xj, this one term I have, plus uj dou rho ui by dou xj. Okay. This is the other term I have. Now, I think I made a mistake somewhere. Rho ui in here, rho uj, ui, rho uj should be kept together. Okay, fine. That's the mistake I made. I am pulling out rho uj instead of rho ui. Okay, otherwise, if of course, it will just confuse you a little bit, but this one will be easier to think about. So, I will keep it as rho uj. Okay. It can be done the other way also, it just does not mean anything because I and j can be switched around, but this is easier to think about. Rho uj as one unit and ui as the other unit. You are going to do this differentiation by parts, and this is equal to minus dou p by dou xi. If I look at this, now I look at just this unit, this is dou by dou xj of rho uj. If I look at this and this, they are exactly the same, except for I is replaced by j, that is all. We will not worry about this I, it might as well be k, and this can also be k. If that is the case, then I am going to say this unit is 0, this unit is 0. Okay. So, this is 0, so I will get my other expression. This is actually a part of fluid mechanics derivation. but I like starting from here, that is all. This is your momentum equation. If I write it in 2D form, these expressions, mass equation will now become in 2D, that is in terms of u and v coordinates. I will substitute for I equal to 1 and I equal to 2. So, I will get u dou by dou x of rho plus v dou by dou y of rho plus rho dou u by dou x plus rho dou v by dou y equal to 0. This is my 2D mass equation for steady flows, steady compressible flows. Now, similarly, I can write momentum equation, but of course, here I will get two equations. It is I momentum equation. So, I will get two equations. U momentum equation will be rho u j can be any value, I is equal to 1 right now, rho u dou by dou x of u plus rho v dou by dou y of u equal to minus dou p by dou x. This is one equation, and the other one, v momentum is going to be rho u dou by dou x of v plus rho v dou by dou y of v equal to minus dou p by dou y. These are my momentum equations, two of them here. How many variables do I have for my flow field? I will now start counting variables. I have pressure, density, u, v. Do I have any other variable? Probably temperature. These are my variables I have to think about. But if I do not think about temperature right now, even now I have only 3 equations. Okay. But I have 4 variables even without thinking about temperature. Temperature also is a part of the problem. Temperature, I know I can use energy equation. Okay. Let us just think about the remaining things. Now I have to link any 2 of them independent of whatever I already linked with. We have one condition in here, isentropic. If it is isentropic, then I can say P by rho power gamma is constant. This is one way of looking at it, or another way of looking at it, this is equivalently given as, I will put dou P by dou rho at constant entropy equal to a square I have, where a is my speed of sound. I will say that this is true for our case. This is always true. Why? We have isentropic flow. So, I am going to say for us dou P by dou rho is equal to a square. I do not need to say only at constant entropy. Our case is fully isentropic flow. So, it is always constant entropy. Okay. So, I have 4 equations. What are the 4 equations? Mass, 2 momentum equations, and 1 isentropic relation. I will use this relation. Okay. Now, how will I use this relation in my momentum equation? I want to remove my dou p variable, but I have dou p by dou x there. So, I will rewrite this as dou p by dou x equal to a square dou rho by rho x and dou p by dou y equal to a square dou rho by dou y. This is the way I will rewrite my expression. What have I done really? It is calculus really. I have taken this, any derivative can be represented as delta p by delta rho, limit delta rho tends to 0. I will take that, I will remove the limit currently, and then I will go back and say I will take this delta rho, multiply it that side. I have this expression without this delta x at the bottom. Now I will divide each side by delta x. Now I will put the limit delta x tends to 0 again. Then I will get to this expression, just calculus rearrangement. The same thing done for delta y, you get to this expression. Okay. That is one way of looking at it, whatever I have done. That is a simple way of looking at it. So, now I will go and substitute for my dou p by dou x and dou p by dou y in my momentum equation. So, I will write it as, I will go back here, what I will do is I will write my a square dou rho by dou x here, and then put that is equal to minus of this whole expression here. That is what I need to do. But I want to do one more extra thing. We want to put this condition irrotationality, which we did not use yet. So, till now my flow, all these equations if I solve will be satisfying mass momentum equation isentropic conditions, that is all. It will not do anything more than that. Now we want to say I want it to be irrotational flow also. How will I force this? I have to tell that I have del cross V equal to 0. Del cross V equal to 0 in 2 dimensions will just come out to be this relation. Now, if you are in fluid mechanics, you will immediately tell that if there is a irrotational flow, now my velocity field can be expressed as gradient of a scalar field. Okay. So, now I can rewrite my velocity field. Okay. V can be expressed as gradient of some scalar field phi. Phi does not have a direction, it is just a distribution like pressure. Pressure is a scalar field, like that phi is some other scalar field. If this is the case, if I know the phi value everywhere in my flow field, that is all the x y locations, then I can get a velocity by doing just the gradient operation on the phi. So, my u velocity will become dou phi by dou x and v will become dou phi by dou y. Am I justified in doing this? Let us do a quick check. We will just substitute this u inside here and this v inside here. What will happen? V derivative with respect to x will give me dou square phi by dou x dou y, and here it will be dou square phi by dou x dou y again, one minus the other. Okay, I will just subtract and it becomes 0. This is assuming phi is continuous in x y, which is reasonable to assume for our kind of flow fields. Okay. So, we are getting this correct. So, we are justified in putting this definition, which we will use like this. Now, I will do one more thing for simplification of our expressions. I will put u equal to phi subscript x. What this means is exactly the same thing as this. Derivative with respect to x is now written as subscript x, just for simplicity, and v is given as phi y, subscript y. If I have this, now we will start using this in our expressions. Okay. I already told you I wanted to substitute dp by dx in momentum equation with this expression. We will start doing all of them together. So, what I will get will be, I will take this dou rho by dou x is equal to 1 by a square dou p by dou x, right. I will go here, dou rho by dou x equal to 1 by a square, with a minus sign put whatever is in the left hand side of my momentum equation. I will write that expression here. What will that expression become? It is u dou u by dou x. That is I am thinking dou p by dou x substitution, right. It is x momentum equation. U is my phi x, dou by dou x of phi x plus phi y, dou by dou y of phi x. Okay. This is what I am having, which now I will introduce more convention. If I put one more subscript there, I will make this phi xx, which means I am taking derivative with respect to x twice, and here I am taking, I will make this phi xy, I am taking derivative once with x, once with y. So, I will write this as minus 1 by a square phi x phi xx plus phi y phi xy, so that the expression looks simpler. Okay, it looks simple enough to handle. We are going to get into very complex expressions, so we want simpler notations like this. Next one I will write dou rho by dou y in similar fashion, and I will skip one step. I will just directly write the answer, minus a square phi x phi xy plus phi y phi yy. This is what you will get. Okay, I skipped this kind of step here, I just jumped one step. Now, I will use these two in my mass equation next. mass equation has dou rho by dou x and dou rho by dou y. Okay. What was my mass equation? I have dou rho by dou x. I will just go back here, I will just tell you what I am doing here and then go back there immediately. I will take this, we have expressions for dou rho by dou x, I have expression for dou rho by dou y in terms of phi, and of course u can be written as phi x, v can be written as phi y, and here rho will keep as of now. Dou u by dou x we know is phi xx, rho dou v by dou y is phi yy. Okay, we can write these things like that. So now we will go and write that kind of a formulation, so that I will skip one step in here again, minus rho by a square times phi x square phi xx plus phi x phi y phi xy plus another phi x phi y phi xy plus phi y square phi yy plus rho phi xx plus rho phi yy equal to 0. These are the last two terms, rho dou u by dou x, rho dou v by dou y are these two terms. If the remaining terms, if I look at these two, they are coming from dou rho by dou x. Okay. Phi x phi xx is there, multiplied by, we had a u here in the mass equation. Yes. Dou rho by dou x.
Yeah, u momentum equation.
In here.
No sir, u momentum equation.
U momentum equation.
That rho term is not present.
I missed a rho term there. Huh? Oh, okay. Dou rho by dou x, I missed a rho term somewhere. Oh, I have it right here, I missed it on the board. Thank you. There should be a rho, yes. It is not just one, there should be a rho in here, yes. Oh, that is why it came up here, that is why you caught it, okay, good. So, this rho is supposed to be there in here. Okay. I missed this, I put it as 1, these two places it should be rho. Now, using that you will get to this expression. The first two terms come from this substituted into mass equation, these two terms come from this substituted into mass equation, and the last two terms are directly in mass equation, the last two terms. Okay. Now, if I look at this expression, density is everywhere in these terms. I know that density cannot be 0, so I can divide by density. Okay. If density is 0, there is no gas, so you will never have that case. So, I will remove my density from my equation, it is non-zero. So, now I have an expression which is just a second order differential equation, non-linear second order differential equation in phi alone, okay, except for I need to know the value of a at every point. It may be changing from point to point, that is also there. Okay. So, now if I think about it, if I want to solve this problem, it is not easy, so I will just go and ask some mathematicians. Okay. And when I go to mathematicians, they ask these things to be expressed in a particular form. They want to group things together as second order terms as the main terms, and remaining things are coefficients to that second order terms, that is the way they want it. So, if I look at these two terms, they are exactly the same, I can just put 2 times this, these two are exactly the same terms. Okay. So, now I will go and rewrite the expression so that it looks like something mathematicians will like. Phi xx 1 minus phi x square by a square plus phi xy minus 2 phi x phi y by a square plus phi yy 1 minus phi y square by a square, this equal to 0. This is some form which mathematicians like. If I look at this, they will directly tell, oh, it is a second order equation, non-linear coupling, okay, great. They will just look at this and say that. Okay. They know how to solve this equation. Okay. All we need to do is go and ask the mathematicians, how do I solve this equation? Okay. before we solve the equation, we have to tell them some more things which we take for granted. We have to tell the mathematicians very clearly. So, we will write two more terms, okay, two more expressions. Du is defined as dou u by dou x dx plus dou u by dou y dy. We are basically giving the relation between du, dx and dy. Okay, that is the idea here. I am giving you a relation between these things, which is probably it's very silly for us in engineering world. Mathematicians want to define these things very clearly, okay, because there can be some nonlinear coupling between this and this, which we will ignore typically. Okay. I can have other terms here, Taylor series expansion kind of thing. I can have a dou u by dou x whole square or dou square u by dou x square kind of terms coming. We will ignore all that right now. Okay. Similarly, dv is given as dv by dx plus dou v by dou y dy. These are the relation between dv and dx and dy. Okay. So, basically I am giving the connection between the velocity field and the spatial field. Similarly, here v velocity field and the spatial field, and we have some other relation which is connecting phi and these things. I will rewrite these expressions in terms of phi, because mathematicians we are going to show only phi to them. If I write that, then it is d of phi x is equal to phi xx dx plus phi xy dy, and d of phi y equal to phi xy dx plus phi yy dy. So, when we go to mathematicians, we take these three equations and then we will tell, okay, these are the expressions I have. There is a system of linear equations, the partial differential equations that are nonlinear. Why is it nonlinear? Because I have phi terms here, and it is already a phi square term here. Okay, it is multiplying those things, so it is not going to be just phi derivative multiplied by phi derivative square. That is a nonlinear kind of term. Okay, that is why you are having it. So, we are going to take these three equations and go to mathematicians, and when we take it to mathematicians, they will rearrange these expressions in a slightly nicer form. I will just show it to you. This is the same expression as before, I just multiplied the whole equation by minus 1. Okay. The next expression they will write will be we will leave that gap for a reason, you will see that immediately. If I think about these gap regions, it is actually plus 0, right, it is equivalent to that 0 times phi xx, that is what this is, it is actually 0. So, this is really not a term, right. Similarly, here we can add 0 times phi yy. So, it looks like it is actually a matrix multiplied by a vector. That is the idea, that is what mathematicians like. So, this can be decoupled into a form where it looks like I have a b c dx dy 0 0 dx dy, this matrix multiplied by phi xx phi xy phi yy equal to 0 d of phi x d of phi y. This is what it is. If I multiply this with this, I will get to that form. That is what you have, okay, where a corresponds to this coefficient here, and b corresponds to that coefficient, c corresponds to that coefficient. Just remember that. So, if I go and show this, I have to actually go to linear algebra people in mathematics, and they will tell me that directly I can solve this problem with Kramer's rule. If we look at this can be solved for phi xx, phi yxy, phi yy from Kramer's rule. Okay. That is, what they do is they will take this column, substitute, say if I want to solve for phi xx, they will take this column, substitute with the first column, find the determinant of that matrix, divided by determinant of the original this matrix. That will be the value for phi xx. Similarly, if I want phi xy, I will take this, substitute the second column, and then do the determinant, that will be in the numerator, divided by this original matrix determinant in the denominator. That will be my phi xy. Like that you can solve for all these three variables. This is our Kramer's rule. Now mathematicians turn around and say, if this is a differential equation of this form, it may so happen that I can decouple this coupled nonlinear equation into an ODE in each of these dimensions x and y separately, okay, or not really ODEs in equations in directions x and y, but in some other directions, some special direction. That can happen if when I solve for phi xy, if my solutions becomes indeterminate. That is, it is of the form 0 by 0. It should become of the form 0 by 0. If it happens, then I can say that yes, I am having a situation where I can decouple the expressions. So we'll look for that for now, and then we'll see if it is working. Before I erase this, there is one condition in this which I did not use till now. I used 2D, I used steady, I used irrotational, I used isentropic. I didn't use m greater than 1. We will come back to it after some time. And of course, remember, I didn't use energy equation. That is also waiting. We will come back to it when needed. By the way, I already told you something extra which says energy equation is not needed. We will get back to you later. Okay. So, I am looking for phi xy solution which is a dx 0, 0 d of phi x, d of phi y, c 0 dy divided by, that is a determinant symbol, divided by a b c dx dy 0, 0 dx dy. Now I have to show that it may so happen that it is 0 by 0 form. If that happens, then my equations can be decoupled. Mathematicians told this, so let us go and try this. If this happens, oh actually before that I will get carried away by that, so I will go back one step. In here, if I go and say that my a tends to infinity in this expression, if my a tends to infinity in this expression, what will I have? This term goes to 0, this part of this term goes to 0, this part goes to 0. So, I will have phi xx plus phi yy equal to 0, which is my Laplace equation, which is my incompressible flow equation on phi, right. So, a tending to infinity means what? I am going to incompressible, that is my waves are travelling extremely fast. If I make a change, immediately flow at infinity knows that I made a change, okay. That is the idea. So, that is also expressed mathematically in this form automatically. If my a is not infinity but anything lesser, I will get to this expression finally. That is the one more thing I wanted to talk about. Now, because of we wanted to get phi xy solution to be indeterminate, which means I want to show that numerator is a 0, denominator is a 0. Now I am going to get two separate equations for this. When I take the denominator alone, we will take the denominator first, we will go to numerator after some time. If I take the denominator alone, I will find the determinant of this, which will be a times this minus 0, a dy square, dx will be minus dx times determinant of this and this, b dy minus c dx. This must be equal to 0, we said. So, look for this. Now, again I will do this divide by dx and then make it a derivative. This can be rewritten as a, I am dividing by dx square and then taking the limit. I will get this expression. What is this? It is nothing but a quadratic equation in dy by dx, which means I can go to a point, I will write the solution for this. This is easy. This is already having a minus sign, you should know that minus of b will become plus b now. B plus minus square root of b square remains the same, minus 4ac divided by 2a. So, I am telling that for that phi xy to be indeterminate, denominator should be 0, of course numerator should also be 0. Currently if denominator has to be 0, then the relation between dx and dy must be this, and we are finding that there are two solutions for it, plus and minus, two solutions are there. So, I am telling my phi xy may become indeterminate only if I move along dy by dx given by this relation. These are called the characteristic directions. That is how you came to method of characteristics, which is what we are dealing with for now. Okay. So, now I have to find these, I have to substitute my original expression in terms of phi x, phi x square etc. for b, a and c. We will do that. If I put that in dy by dx equal to, our b was 2uv by a square. I am rewriting it in terms of u and v, where this was actually phi x phi y by a square. I am putting it back in terms of u and v, plus minus square root of again b square, which is 2uv by a square whole square minus 4 u square by a square minus 1 into v square by a square minus 1. I am replacing all phi x by u and phi y by v, I am doing that inside here. So, I am getting this particular relation divided by 2a, 2 into u square by a square minus 1. Now, if I look at it, I have 2 here, 2 here, 2 square inside a square root, 4 here inside square root. I can cancel all of them. Now, only the remaining thing I need to think about. Okay. So, I look at this, it is going to be uv by a square plus minus, let us say we will look at it in a simpler way, we will just look at what is inside the square bracket, square root. Inside the square root, it was b square minus 4ac term, this is equal to u square v square by a power 4 minus, multiply these two things, which is again u square v square by a power 4, this into 1, that will be plus u square by a square, and this into 1, that is again plus v square by a square, and then this 1 into this one with the minus sign, minus 1. These two get cancelled. Now, we know it is in 2D problem, u square plus v square is my total magnitude square. So, I can write this as capital V square by a square minus 1, which is our m square minus 1. Okay, I get to this form. Now, I will go back and look at my dy by dx expression. I am saying inside the square root, I am going to have m square minus 1 finally. If this is m square minus 1, it can have a possibility of going negative, right? If Mach number is less than 1, my square root goes negative, which means I do not have really a real dy by dx direction. It is going to be complex, which means it is not real, it is not true. So, dy by dx does not exist. For m less than 1, okay. But if it is equal to 1 or greater than 1, dy by dx exists, and if it is greater than 1 alone, then I have two separate values for dy by dx. If it is equal to 1, I have same value twice, that is what I have, okay. If dy by dx two real values for m greater than 1. This is where I am going to use my m greater than 1 assumption, which I did not use till now. I am going to say I want to solve for supersonic flow alone, no subsonic flow in my flow field, then I can go directly into this part. Then I will say yes, I have this particular condition. If m equal to 1 happens, then that is not really bad. It so happens that the two values will be the same value. So, I can might as well add this to be m greater than equal to 1 in here. Okay. We still have not found the value for dy by dx, we did only halfway, we have just done what is inside the square root, we have to do the remaining terms, we will do the remaining also now. So, we will go back and look at dy by dx. It was uv by a square plus minus square root of m square minus 1 by u square by a square minus 1. Now, I will say I will go back and convert uv coordinates to v theta coordinates, that is magnitude of vector and direction of the vector. So, I can write u equal to v cos theta and v equal to capital V sin theta, and write this. Now, I will substitute this inside there. So, I am going to get, and I know that v square by a square, which will come from here, will be my m square. I will write that also in there. So, it will be m square cos theta sin theta plus minus square root of m square minus 1 divided by m square cos square theta minus 1. Now, we want to look at that m square again. We want to write m equal to 1 by sine of Mach angle, which is true, right? We defined the sine of Mach angle to be 1 by m. So, it is going to be this. This was, I believe, around the 4th class or 5th class of our course. Anyways, we did this Mach cone, comes out to be this. We will define it like this. Why? We will go and see the reason later. It simplifies the problem, that is why. Okay. We will do this. Now, if I do this, my m square will be 1 by sine square mu. So, now I can write my dy by dx as cos theta sin theta by sine square mu plus minus square root of m square minus 1 divided by cos square theta by sine square mu minus 1, okay. Which of course, now I can rearrange this a little bit, okay. And by the way, I can substitute this m equal to 1 by sine mu also in my m square here, which will be m square minus 1 equal to 1 by sine square mu minus 1, which will be 1 minus sine square by sine square, which is my cot square mu, becomes cot square mu. Square root of that will just become cot mu, and then I will multiply it with sine square mu in the numerator and denominator, which will give me a final form cos theta sin theta plus minus cot mu multiplied by sine square mu will be cos mu sin mu. Divided by denominator also multiplied by sine square mu, which will be cos square theta minus sine square mu. Yes, it doesn't look any more simpler than this. So after this we will go to mathematicians and say simplify this. Actually it is just trigonometry and algebra, we can simplify it. I will just skip that for this course, it will probably take half a class to do that. We will skip that and we will just directly jump to, now you know why we wanted to substitute m in terms of mu. Finally you get to this form. If we go through that half a class of derivation, you will end up with this form. Dy by dx will give me two solutions, tan of theta plus minus mu. Plus will be one solution, minus will be another solution. We get two solutions. This is just one part of the problem. We go back to our determinant, we still have to look at the other part. The numerator should be 0 now. We are done. If I give the relation between dy and dx to be that particular dy by dx equal to tan of mu plus theta, or tan of theta plus mu and theta minus mu, then I will get two different directions along which my denominator is 0. Now I have to make the numerator 0. We look at that now, and the numerator, if I look at it, that gives me, determinant of that is going to give me okay, I am going along one of those directions, multiplied by minus c dx equal to 0. You get to this particular expression. This is the determinant of that particular thing. Okay. If I rearrange this, where I will again substitute, this is my u, this is my v, I will get to a form where dv by du is equal to minus a by c dy by dx. I get to this particular form. Okay. Of course, we already know from denominator determinant 0 that dy by dx can take two values. So I have to actually think about dy by dx 1 or dy by dx 2, which means again I am getting two relations. For each of the dy by dx direction, I have one equation. Like that, I have two separate conditions between dv and du. I get. Okay. That is the idea now. Now I am going to tell that if I get this expression, and this is just a number now for us, right? I can substitute this in terms of u and v, I can substitute this in terms of u and v, and simplify this, which we will do next class of course. Okay. But when we do that, you will find that the equation becomes ordinary differential equations, which is the idea of this. Okay. We started with something very complex, nonlinear coupled partial differential equation of second order. Finally it came down to simplified version for m greater than 1 alone, not for m less than 1. Okay. And this is what we want to solve anyway. We want to solve supersonic flow field currently. We find that this particular method, if I move along some characteristic direction, things become simpler, which is what we want to look at. The remaining part we will do next class.